Hello guys, so welcome to our last lab, lab 10, in which we're gonna explore the amplifiers or NMOS amplifiers, common source, common gate, and common drain. Okay, so this lab or this recording will be divided into 3 parts or 4 parts. In the first part or first experiment, we're gonna explore common source amplifier. In the second recording or second part, we're gonna explore common source amplifier with a source resistance, like for example the degenerate resistance RE in BGT amplifiers. The third part, we're gonna explore a circuit of a common drain amplifier. Then finally we will get to the common gate amplifiers. Okay, so let's start by common source amplifier. So here is experiment 1. But before we go to the lab itself, Multisim, and implement it and simulate it, we're gonna first analyze it by paper and hand. Let's get an idea about how much would be the current, the DC voltages and the DC current, and also the amplification. Okay, before we get to the result, just to make sense of the results that we get. So let's start first by the DC analysis, which is very important to check first that we are really running in the saturation region, and also to get GM or to calculate GM. Okay, so let's check first if this is really a common source amplifier. So here is the input, is at the gate, and the output is at the drain, and the source is just common between them. So it's really a common source amplifier. Okay. So for the DC analysis, all the capacitors will be open circuit. So just to forget about, this part, which is input parts are signal and V signal. Also forget about the load part. Also forget about this capacitance. Okay, it will be open. And you will have only the voltage divider and RD, RS, and the transistor itself. Okay, this transistor has Kn equal to 10783 milliampere volt square, and V threshold equal to 2. This is very important in order to conduct the DC analysis. So first, we need to know ID and VGS. Okay, so we will assume it's a saturation. It will be saturation eventually, but let's assume it's a saturation. Okay, so ID equal to Kn over 2, then VGS minus V threshold square. So we have here 2 unknowns, which is ID and VGS. So we need another equation that relates both together. So this is the equation. Will come from this loop here. You have the voltage across the resistance IDRS. You have VGS here, and you have VG. So from, let's call it loop 1, for example. From loop 1, VG is the voltage at the gate here, equal to VGS plus ID RS. RS is known, VGS is known, unknown also. ID is unknown, so 2 unknowns here. But how about VG? So VG, that the current cross going into the gate is 0. So RG1 is in series with RG2. So VG is actually 10, which is VDD, multiplied by RG2, which is, let's write it, RG2 over RG1 plus RG2, equal to 10. And RG1, RG2 is 200 kilo ohms over 200 kilos plus 300 kilos, which is 500 kilos. So basically 2 zeros will go with these 2 zeros. This is by 1, this is by 2. So VG is actually equal to 4. Okay, so from that equation here, we can write that ID equal to RS is 2 kilo ohms. RS, right, 2 kilo ohms. So we can divide by 2. So 4 divided by 2, which is 2, minus VGS over 2, which is half VGS. Okay, good. So ID is also equal to this term here. So 2 minus half VGS equal to Kn over 2 VGS minus V threshold. And let's just, substitute for V threshold because it's known, it's 2. And let's also, substitute for Kn, which is also known, it's 100.783 milli. Okay, and whenever you have equation with current in milli, usually the Kn should be also in milli, and the resistances are in kilos here. Okay, so don't worry about the milli as long as your resistances are in kilo ohms. Okay, so basically, guys, we have here this equation. So 2 minus half VGS equal to 100.783 over 2, and here is VGS square plus 4 minus 4 VGS. Okay. We can multiply both sides by 2. So this will be 4 minus VGS equal to 100.783 VGS square plus this would be 4 multiplied by this. So let me so we can reduce this equation here to that form. Okay, you just combine the terms that has VGS together and the constant term is also together. You will get to this equation here. Then by solving this quadratic equation, you will get two solutions. VGS is equal to 2.14 and VGS is equal to 1.85. We should choose one of them, of course. Okay, and the one that is logical here is that one. Why? Because it's larger than V threshold. Remember, V threshold is equal to 2. This guy is less than V threshold. And if VGS is less than V threshold, then the circuit will be, the transistor will be off. Okay, so this one is also is rejected, and we will take the first solution, which is 2.14. It's actually 2.135, but I just make I just make approximation here to make it 2.14. Okay, so VGS is equal to 2.14. Now we should calculate ID. Okay, so let's. Now we calculate ID. ID is calculated from that equation. It's equal to Kn over 2 VGS minus V threshold square. Okay, so we get that 2.14 and this guy is 2 and we know Kn. So if we just compensate it, we will find that it's approximately 1 milliampere or 9.99 milliampere, which is approximately 1. Okay, now we know the DC analysis. We know ID, we know VGS. Now let's calculate GM. GM is equal to Kn VGS minus V threshold. Okay, and if you do the calculations here, it will be around, let's do it again. It will be 7.05 milli ohm minus 1. Okay, and now let's verify that we are really working in saturation. So we can calculate VDS. from that big loop here. So from that branch, you know, the voltage across RD, the voltage across the transistor VDS, plus the voltage across RD equal to VDD. So VDD, which is 10, equal to ID. Let's calculate it as 1 milliampere. So RD 1 multiplied by RS plus VDS plus 1 multiplied by RD. So 10 equal to RS is 2 kilo multiplied by 1 milli, it will be 2. RD is how much? RD is 5 kilo multiplied by 1 milli, it will be 5. And VDS here is unknown. So from here, VDS is equal to 10 minus 7, it will be 3 volts. And VDS is larger than VGS minus V threshold because this guy is 3 and VGS is 214 minus 2, which is 0.14. So we are in saturation. Okay, now let's go to the AC part. So in the AC analysis, we're gonna draw the equivalent circuit. Okay, of the let's start with the transistor first. So the transistor have GM VGS. Here is the drain. Here is the source. Here is the gate. The source is connected to ground because when we short C2, RS will be shorted. So the source will be connected to ground. Then the drain is connected to ground through two resistors, RD and RS, and RL, I'm sorry. Here is the output. And the gate is connected to ground through RG1 and RG2. Let's name them RG. And here is VGS, by the way, on the open circuit. Here is RG. And before we forgot, RG is RG1, parallel RG2. And 200 parallel 300 kilo is 120 kilo ohms. Also, we have our signal and the signal. Okay, and here is the input. Okay, now let's get EV and other stuff. So EV equal to VO over the input. VO is the current through RL and RS multiplied by the parallel combination of them. And this current is GM VGS, so minus GM VGS. RL parallel RS. I'm sorry, this is RD, not RS. This is RD. Okay, and why minus? Because the current is flowing from bottom to up, so the voltage drop is positive negative versus negative positive for VO. And V input is actually the voltage between the gate and the ground, or the gate and the source, right? Because the source is connected to ground. So it's equal to VGS. So VGS will go with VGS. So this will be equal to minus GM RL parallel RD. So EV, if we calculate, we have GM already, right? It's 7, yeah, 7. We have RL, we have RS, so this is equal to minus 7 point something very small, 05, multiplied by RL is 5 kilo ohms, and RD is also 5 kilo ohms. So the parallel combination of them is 2.5. And remember, this is in milli ohm minus 1. This is in kilo ohm. So this will go with this, and this will go with the milli. So we are fine. So 7.05 multiplied by 2.5. Let's do it very quick. 7.05 multiplied by 2.5. It's 17.625. Okay. This is EV. How about GV? GV is equal to AV multiplied by our input over our signal plus our input. GV is 17625. Our input is the resistance that the signal source sees. Signal source, I mean here by the signal voltage itself and the internal resistance. So it's actually between the two terminals of the input. Okay, and in that case, it's RG. So our input is RG, and our signal in our case is 120 kilo ohms. So GV is equal to 17625. RG is 120 kilo ohm, and our signal is 120 kilo ohm, so it's half. So 17625 multiplied by half. So let's do that very quick. Just multiplied by half here. It will be 8.8125. And of course, negative. Okay. GV always carries the same sign as EV. Okay. Now we can expect what kind of number we get for VGS. It should be around 2.14. We should get a current around 1 milliampere. We should get EV around 17.6. We should get a current, overall voltage gain equal to 8.8. And of course, there should be inverting output because AV and GV are negatives. Okay, so let's do now the experiment itself. Okay, but before doing that, we're gonna explore or highlight what's required from the data sheet, from the lab manual. So let's share the other screen now, which is this one. Okay. So here is the lab manual. So we have 4 experiments. The first one is studying the amplification characteristics of common source amplifier, and here is, our circuit. Okay. So after running the circuit, or running the simulation, we're gonna put here the measurement for ID, VG, VS. Of course, if you know VG and VS, you know VGS because it's a subtraction of them, and GM. And here you put the theoretical value. As you will see, the error will be very small. Okay. Then we check the waveforms of the input here. This is the input. This is not the signal. The signal, we know it's a constant. It's our input. It's a 20 millivolt peak to peak or 10 millivolt peak. Okay. And we should see here, half of this because the input is equal to the signal multiplied by our input over our input plus our signal. So the voltage at that point, the AC voltage at that point here should be half of this one. Or GV should be half of AV. That's it. Okay. So we're gonna set the parameters of the CRO to these settings. Okay, for the scales for channel A, channel B, and the time. Then we put here, in this placeholder, the output waveform, the input versus the output. Then we calculate the voltage gain. So from the CRO, we measure using the markers. We measure the voltage peak to peak of the output at that point, and the voltage peak to peak of the input at that point. Then we can just calculate EV or measure. This is of course the measurement of EV because it depends on measurement values of the output and the input. We can also calculate the overall voltage gain without making such analysis because we have the CRO. We have already the output. We are sure about the input. It's a source, and in Multisim sources are can be said to be ideal. So the input voltage is 20 millivolt peak to peak. So you need just to divide the output voltage that you get, that you measured, by 20 millivolt. Okay. Then you calculate the theoretical value of EV. We just made it now, minus GMRL parallel RD, which is, it should be minus 17.625. And you should compare here the values together. Okay, and you should here answer why GV equal to have AV, and I already did this with you guys in the notes, because of course our input have the same value of our signal, so our input over our signal plus our input is just half. Okay, of course if our input is much larger than our signal, then GV will be approximately equal to AV, 1 AV. Okay, good. So let's do the circuit now. So let's go to the multisim itself. Here is multisim. Okay, one new thing here that I did is this VDD. So instead of adding a battery and setting its value or voltage, you have the option to add a VDD. So you just make place component because it's running, so it can't. So place component in the sources here, power sources. You have here something called VDD. It's just like a battery, it's nothing new, but it makes your drawing, or circuit much more readable. So nothing new. If you want to make it with a battery, that's fine. Okay, you just connect the battery here, making the positive terminal connected to this node, and the negative terminal connected to ground. Okay, good. So let's run this and check what is VD, what is VG, what is VS, all such stuff. So here is VG, the voltage at that point. It's 4 volts, just like the value that we anticipated from the analysis. What is VGS? VGS was 2.14. It's actually 2.1435. If you just make it very precise, okay. But I just make a rounding for this 5, for this 4, and make it for this 3 and make it 4. So it become 2.14. Here I didn't measure VGS directly, although you can do this using this probe here. You can have a differential probe. So this probe has 2 terminals. You put one on VG, one on VS, and it will give you the difference. So, but we can add 2 probes and that's it. So this probe is measuring 1.86, and this probe VG is measuring 4 voltage, 4 volt. So if you subtract 4 minus 1.86, it will give you 2.14. That's it, which is exactly the same values that we get from our analysis. Okay, the current we get it as approximately 0.99 milliampere, or we can say 1 milliampere, and here it's 0.932, okay, ampere, or 932 microamperes. They are both equivalent. Of course, there is some error here in the but it's still small, still very small, 0.06 milliampere. Okay, good. So let's now measure VO and V input. So VO is the one with the cyan color, V input is the one with the red color. So here is the red color, which is it should be V input, right? So let's measure it. Let's measure first V output, that's fine, which is the cyan color. So V output here is, it's a channel A, yeah, 321, yeah, 321.26 millivolt. Okay, and as you see, it's inverting. The output is out of phase with the input. This is a characteristic of the common source amplifier. How about V input? So let's change now the markers. It should be 10 millivolt, right? Because we said that the voltage at that point, it should be half of that input. So let's measure it. So the red, yeah, the red is our V input, and I think we are at the maximum here. So yeah, it's 9.388 millivolt. Okay, so it's around 10 millivolt. One thing here to notice, guys, the input is not bigger than the output. No, the scale is different. So let's change the scale. So let's make the scale of the output a little bit bigger. Look, this is at 50 millivolt. If I make this 50 millivolt as well, it will be very small. Look, very small. Okay. And let's verify EV. EV should be 17.6, right? So the output is peak to peak is, let me do it very quick with you, 321.345 millivolt over 9.388. It is, yeah, it is 34. Looks like we made some mistake with GM, I think. Yeah, I have a mistake with GM. So GM is actually, I'm sorry, GM should be 14.100. So when I calculate GM, so let's go back here to correct this with you guys. Yeah. So here, when I calculate GM on my calculator, I make it Kn over 2, which is wrong. Okay. ID is equal to Kn over 2 VGS minus V threshold square. But GM should be just Kn directly. So this will be 14, just the double of this number. So we are not. So this should be 14.1. Yeah. So basically we should correct as well AV. So this is 14.1 multiplied by 2.5. So let's do it very quick here. 14.1 minus 2.5. It should be 35.225. So good. $35.25. So basically, GV will be 17.6. Remember, because GM is doubled now, so AV is doubled, so GV should be doubled. So GV should be 17. But let's make it so we're gonna just remove the old value of AV here, and also here. And also here. So I'm gonna put 35.25, 35.25, 35.25. So this will give you, of course, 17.6 something. The old value of AV. So if you do it very quick here, multiplied by half. Yeah, 17, like what I said, 625. Okay, and from our analysis now, we found that the output is 321.345 millivolt. If we divide it by 9.388, it will give you 34. Okay, so if you go back here to the so this guy, the output, which is a Cayenne, is 300 millivolt. If we divide it by 9.388, if you do it by yourself, it will be 34.22. It's very close to 35.25. Okay. How about GV? You have now the output, which is 321 millivolt. Just divided by 20. Of course, it will be doubled, almost double. So if we divide, let's do it, by the way, no problem. So if we divide 321.345 by 20 millivolt, it will be 16.06. And we have the theoretical values that we calculated just now, 17.625. Of course, there is an error, okay, but very small one. Okay, guys. So that's the conclusion of experiment 1 or record 1. Now we go to experiment 2, the second recording, which would be the same circuit, but including RS. Okay, in the AC analysis. Okay, guys. See you in the next recording.